I'm going to talk about the mathematics of a solar eclipse. So it's geometry, which is why I feel like I can do it in this class. So, of course, we can start with this sort of standard geometric picture of what an eclipse is. So the sun, the moon, and the earth line up in a row. And so because the moon is between the sun and the earth, it blocks the sun's rays and casts a shadow on part of the earth. So there it is. So that's the geometry of the eclipse. So the real questions I want to ask are twofold. One, why do we have eclipses at all? And two, why don't we have more eclipses? So let's look at this a little bit more carefully. So as you know, the Earth goes around the sun in an orbit which is approximately circular, but actually sort of elliptical. And the fact that the path of the Earth around the sun is an ellipse is a consequence of Kepler's laws, which are related to the mathematical laws of Newton. And in particular, one of the Kepler laws is that the motion lies in a plane. Okay, this is actually a consequence of conservation of angular momentum, that there is a momentum vector, and the momentum vector is perpendicular to this plane of motion. You may have seen that derived in Math 3, I don't know. Anyway, okay, the Earth orbits the sun. Now, of course, likewise, the moon orbits the Earth. And again, the motion lies in a plane. Now, the question is it the same plane? Well, if it was the same plane, then it's pretty easy to see that we would get an eclipse basically every month. In fact, we get a solar eclipse and a lunar eclipse every month. Right? I mean, this picture makes it pretty obvious that they're going to line up every month. So we'd have lots of solar eclipses. Okay, but it turns out they're not in the same plane. So in fact, the plane of the moon and the plane of the sun make a rather shallow angle of about 5 degrees. So now we get a little Euclidean geometry. If you have two planes and they're not parallel, they meet and their intersection is a line. So here's a picture. So the yellow plane is the plane of the Earth and the moon, and the whatever color that is, purple plane, is the plane of the Earth and the sun. Okay, so now we have a little problem in this picture, because if you have three objects in three-dimensional space, they lie in a plane, but they don't generally lie on a line. And in fact, in this picture, they can't possibly lie on a line. So this picture says there isn't going to be an eclipse, because if there was a line containing all three objects, then that line would have to lie in both planes, because any 2 points determine a line lying in every plane that contains those objects. So, as long as the sun does not lie in the intersection of those two planes, there can't be an eclipse. So, here's a picture to indicate when an eclipse is possible. The line of intersection of those two planes would have to pass through the sun. Of course, the line is guaranteed to always contain the Earth because the Earth is in both planes. So, as the Earth moves, here's the critical issue. The line of intersection moves parallel along the plane containing the Earth and the Sun, which is called the ecliptic plane. So that's this picture. Now, it needs a little bit of explaining why the line of intersection is always one of these parallel lines. And the reason is really conservation of momentum, because, as I said, the plane of the Earth and the Sun is perpendicular to a certain vector, which is conserved. And likewise, the plane of intersection of the Earth and the Moon is perpendicular to a vector. And that's fixed. That is, relative to the universe, the vector always points in the same direction. And the line of intersection is perpendicular to both. And so, if you like, you can take the cross product of the two vectors that I'm talking about, and that'll give you the direction of the line, and that doesn't change. So as the Earth goes around the Sun, that line moves so that at any time it is positioned somewhere on the orbit, and the line goes through that point on the orbit. Okay, that's the key fact that you need in order to understand. Because it means that twice a year, the line is going to pass through the sun. The line is going to move up and down and up again. And so, there are exactly 2 times in the year when this occurs. And those are called eclipse seasons. So here's an arrow pointing to one of them, and there's the other one. So there are 2 particular times in the year when it's possible to have an eclipse. So if we localize this picture now, so I'm not showing you the sun, if we're during the season, is along that line. And so this is a picture of the moon's orbit, and you see that the moon's orbit hits that line in 2 points. So those are called the nodes. So whenever the moon is in one of those 2 positions, there are going to be 3 objects lined up in a row. And of course, which one is which? Well, on this side, if the sun is over there, then on this side, what you're getting is a lunar eclipse. And on the other side, you get a solar eclipse. So the conclusion is that there should be an eclipse every month of the 2 seasons. Well, if the sun, the moon, and the earth were points, which is an idealized version of the mathematics here, you'd only expect 1 eclipse during a season. But actually what can happen, since they only almost line up, is that you can have 2 partial solar eclipses in the same month. And I'm sorry, in the same season in consecutive months. And so it turns out, interestingly enough, that there are between 2 and 5 solar eclipses every year. Now, they tend to be partial eclipses, especially when you have multiple ones, but there are going to be some kind of eclipse 2 to 5 times every year. Yes?
There can't be one eclipse.
Well, there's one eclipse in each season.
Oh, yeah.
So, right. I don't really fully understand how you get 5. It seems like you shouldn't get more than 4, but apparently we sometimes get 5. So that's my explanation of why we have eclipses and why we have the number of eclipses we have. I just want to finish with a couple of interesting remarks. So, as I've said, the fact that this plane moves parallel is a consequence of a law of physics, which, by the way, you can also think of as a law of mathematics, depending on your view of physics, is mathematics, conservation of momentum. But the fact that total eclipses occur, total as opposed to partial eclipses, is a consequence of a remarkable coincidence. And the coincidence is the sun's distance from the Earth is 400 times the moon's distance from the Earth, and the sun's diameter is 400 times the moon's diameter. And because of that coincidence of these 400s, it's possible for this picture to occur. In other words, if you look at this as similar triangles, okay, here I've sort of exaggerated a little bit, but this is essentially right. You draw the tangent lines from the center of the Earth to the sun, and the tangent lines from the center of the Earth to the moon, and if they line up, then, as this picture shows, the moon can completely block out the view of the sun, in which case you get a total eclipse, which I believe is what we're going to see in April. So that's, I can't explain it except to say it's a wonderful miracle. Now, sometimes, depending on where the moon is, you get a partial eclipse, and sometimes you get one of these ring eclipses where you see the outer edges of the sun around the moon when the moon is completely blocking it. Because keep in mind the relative distances change a little bit depending on the particular event. So it turns out there is a total eclipse somewhere on Earth roughly every 18 months, which you may find kind of surprising because they seem so rare. But there's a total eclipse somewhere roughly every 18 months. But if you're in one particular part of the Earth, like Cleveland, it's very rare that it happens. And that's why, on the one hand, we have an unexpectedly large number of eclipses, and on the other hand, we have such a small number of eclipses. It depends on where you happen to be. Okay, any questions? Yes?
What are the actual chances of having an eclipse? Do you know?
They're 100% this year.
Well, I mean, just generally. Rare.
Okay, I don't know the answer except to say that it's probably something that only happens at least no more than once in several centuries, probably more than that. But that's outside my area of expertise.
I mean, if you consider that like the eclipse could really just happen anywhere over the Earth, Probably most of the time it's going to happen on the ocean. Or if it's-
Yes, that's right. That's why we don't see most of them, unless you're one of those people who likes to charter private jets just to go out to the middle of the ocean to see an eclipse, which I guess you could do.